Welcome to ReneEnergy.com, your renewable energy and sustainability platform. Greetings from ReneEnergy.com, your go-to resource for all things renewable energy and sustainability. Hydrogen, often dubbed as the fuel of the future, presents a paradigm-shifting promise to revolutionize not just transport but multiple sectors. However, like any nascent technology, hydrogen is not without its impediments. This extensive discussion aims to dissect these multidimensional challenges through a sector-by-sector analysis. From automotive and industrial applications to energy storage and aviation, we will scrutinize what's stalling hydrogen from becoming the fuel of tomorrow. Brief overview of hydrogen as an energy carrier. Hydrogen is often referred to as the fuel of the future due to its abundant availability and clean combustion properties. When used as an energy carrier, it holds the potential to power a wide range of applications across various sectors, from transportation to industry. Moreover, hydrogen can be produced from a multitude of sources, including water, organic matter, and even fossil fuels, offering considerable flexibility. Despite its promising features, hydrogen's role in the current energy landscape is relatively limited, primarily due to a host of challenges that encompass technical, economic, and logistical factors. This video aims to delve deep into these challenges, exploring the complexities that have hindered hydrogen's growth as a reliable energy carrier. Automotive applications, the road less traveled. High fuel costs. The cost of hydrogen fuel stands as one of the most formidable barriers in the automotive sector. While hydrogen can be produced through several methods, such as steam methane reforming or electrolysis, both options incur substantial costs. With current technology, the price per kilogram of hydrogen is high, and considering that a typical hydrogen fuel cell vehicle requires around 5 to 6 kilograms for a full tank, the numbers add up quickly. As a result, the total cost of ownership over the vehicle's lifetime can be significantly higher than other fuel options, dissuading potential buyers. Limited infrastructure. In regions like California, where hydrogen fuel cell vehicles have seen the most adoption, the infrastructure remains sparse and unevenly distributed. The high costs associated with setting up hydrogen refueling stations, from land acquisition to installing complex storage and delivery systems, have limited their proliferation. Consequently, hydrogen vehicles are often confined to specific geographic locations, making them less versatile for long-distance travel or daily commuting in areas without infrastructure. Volumetric energy density. Hydrogen's low volumetric energy density is a considerable challenge in automotive design. A hydrogen fuel cell vehicle needs a large and robust storage system to contain enough hydrogen for a practical driving range. These storage systems often have to operate at extremely high pressures, around 700 bar or 10,000 pounds per square inch, to store sufficient fuel. This necessitates large, heavy tanks that can take up a considerable amount of vehicle space, compromising on passenger or cargo space, and affecting vehicle design. Resale value. Hydrogen vehicles have historically suffered from rapid depreciation. As newer models with better technology enter the market, older models quickly become obsolete. The limited availability of refueling infrastructure also impacts resale value, as the cars are less practical for potential buyers living in areas without easy access to hydrogen. Furthermore, concerns about the long-term reliability and maintenance costs of hydrogen fuel cell systems can also reduce resale prices, making these vehicles a less attractive financial investment compared to more established types of vehicles like gasoline or electric cars. Industrial applications, high stakes, high costs. Production costs. Producing hydrogen is far from inexpensive, particularly when considering methods that yield high purity levels needed for industrial uses. The most commonly employed method, steam methane reforming, SMR, involves high operating temperatures and pressures, necessitating a large energy input. Though relatively efficient, the method also produces a significant amount of CO2 as a byproduct, undermining the clean energy credentials of hydrogen. Green hydrogen. The concept of green hydrogen, which is produced through electrolysis using renewable energy, offers a more environmentally friendly alternative to SMR. However, challenges remain. Firstly, electrolysis is an energy-intensive process. The efficiency rates rarely exceed 70 to 80%. For this method to contribute positively to the climate agenda, it's essential that the electricity used comes from renewable sources, which is not always the case given the current energy mix. Also, the equipment costs, such as the electrolyzer, add additional financial burdens to green hydrogen production. As of now, green hydrogen remains significantly more expensive than its conventionally produced counterpart. Storage and transport. Once produced, hydrogen's low volumetric energy density complicates storage and transportation. Hydrogen gas needs to be stored either at high pressures or at very low temperatures, both of which incur substantial energy and financial costs. For instance, cryogenic storage at temperatures as low as -253 degrees Celsius is highly energy intensive. High-pressure storage, on the other hand, necessitates specialized, heavy, and expensive tanks. These factors add logistical complexity to industrial applications, where the need for large volumes is often the norm. The storage and transportation hurdles significantly impact the cost-effectiveness and practicality of using hydrogen in various industries, ranging from high-tech sectors to traditional manufacturing. Until effective solutions for these challenges are found, hydrogen's adoption in the industrial sector will likely remain limited. Aviation applications, the high-flying dream. Volumetric energy density. While hydrogen boasts a higher gravimetric energy density compared to conventional jet fuel, its volumetric energy density is much lower. This creates a massive design challenge for aviation engineers. Conventional fuels like JP8 are energy dense and occupy relatively small volumes, which is a crucial attribute for an environment where weight and space are highly restricted. For hydrogen to be used as an aviation fuel, much larger storage tanks would be needed, affecting the aircraft's aerodynamics and weight distribution. This presents a significant technical hurdle that hasn't been fully overcome yet. Safety concerns. Safety is of the utmost priority in aviation, and hydrogen poses particular risks. Its flammability range is far wider than that of conventional jet fuel, meaning it can ignite at a broader range of concentrations and conditions. Furthermore, storing hydrogen requires either cryogenic temperatures or high pressures, both of which present additional risks of leaks or other failures. As such, the safety systems around hydrogen storage and delivery would need to be extremely reliable, likely requiring redundant safety mechanisms that could add weight and complexity to the aircraft. Aircraft design. The unique properties and challenges of hydrogen would necessitate a complete overhaul of existing aircraft designs. This isn't a matter of simply retrofitting existing aircraft. Entirely new designs would be needed to accommodate the low volumetric energy density and unique safety concerns of hydrogen. The wings, where fuel is typically stored, may not be sufficient for hydrogen storage, requiring a rethink of where and how fuel is stored on the plane. This kind of design change is not only expensive but would also require an extensive period of R&D, testing, and certification, stretching over years, if not decades. The complexity of these challenges highlights why hydrogen has not yet been widely adopted as a fuel source in aviation. Despite its promise, these hurdles are far from trivial and will require a concerted effort from engineers, researchers, and policymakers to overcome. Energy storage, power to gas, the inefficient middleman. Efficiency loss. Hydrogen is often considered for its potential in energy storage, particularly in power-to-gas systems where excess electricity is used to produce hydrogen through electrolysis. This hydrogen can then be stored and later converted back to electricity when needed. However, this process is fraught with efficiency losses. Each conversion step, from electricity to hydrogen and then back to electricity, involves energy loss. These losses make the entire process less efficient compared to direct electrical energy storage methods like lithium-ion batteries. Furthermore, the efficiency loss becomes particularly significant when we consider grid-scale energy storage, where even small efficiency differences can translate into substantial energy and financial costs. Economic viability. Cost is another significant barrier to hydrogen's role in energy storage. The technology involved in hydrogen production, storage, and reconversion to electricity is generally more expensive than other energy storage solutions, such as pumped hydro storage or lithium-ion battery arrays. These economic challenges make it difficult to justify the investment in hydrogen-based storage systems, particularly for grid operators who are usually constrained by tight budgets and high reliability requirements. The absence of robust subsidy programs or incentives further hampers the economic viability of hydrogen for large-scale energy storage. Infrastructure. Storing large amounts of hydrogen safely and efficiently is an infrastructural challenge. The gas requires either high-pressure tanks or cryogenic temperatures for liquefaction, both of which have their own sets of problems. High-pressure tanks are expensive and can be dangerous if not managed properly. On the other hand, cryogenic storage requires a consistent energy input to maintain extremely low temperatures, which could offset some of the efficiency gains in a renewable energy system. There's also the issue of transport. Getting the hydrogen from the production site to where it's needed for reconversion into electricity or other uses could involve pipelines or trucking, both of which are fraught with their own sets of challenges and inefficiencies. In summary, while hydrogen holds promise as a medium for energy storage, there are considerable challenges in terms of efficiency, economics, and infrastructure that must be overcome for it to play a significant role in future energy systems. General challenges, the bigger picture. Public perception. The use of hydrogen as an energy carrier has to contend with various misconceptions and negative public perceptions, some of which date back to incidents like the Hindenburg disaster. While technology has advanced significantly since then, the perception of hydrogen as a risky and complicated option persists. This notion can slow down the adoption of hydrogen technologies by causing hesitation among consumers and investors. Overcoming this barrier requires not just technical advancements but also concerted public relations efforts, education, and a proven safety record to change the narrative around hydrogen. Policy and regulation. Hydrogen's growth as an alternative fuel or energy storage medium is also inhibited by a lack of cohesive policy support. While renewable sources like solar and wind have enjoyed various subsidies, tax incentives, and favorable regulations, hydrogen has often been left out of these beneficial policies. In some cases, existing regulations can actively hinder the deployment of hydrogen infrastructure, such as refueling stations or pipelines. Coordinated policy initiatives that are specifically designed to promote hydrogen could catalyze its adoption across different sectors. Economic factors. Market forces also play a crucial role in the adoption of hydrogen technologies. Without a critical mass of users in any sector, it becomes difficult to justify the investment needed for building the necessary infrastructure. This creates a classic chicken and egg problem. Consumers are hesitant to adopt hydrogen technologies due to the lack of infrastructure, while stakeholders are hesitant to invest in infrastructure without a guaranteed user base. This cycle can only be broken through external interventions, such as government incentives or groundbreaking technological advancements that significantly lower costs or improve efficiency. Environmental concerns. While hydrogen is often promoted as a clean energy carrier due to its zero-emission combustion process, the methods for producing hydrogen are not always environmentally friendly. Currently, most hydrogen is produced through steam methane reforming, which emits a significant amount of CO2. Even when produced via electrolysis, the electricity used is often sourced from non-renewable means, negating some of its environmental benefits. For hydrogen to be truly green, advances must be made in sustainable production methods, including the use of renewable energy for electrolysis. In conclusion, while hydrogen has the potential to significantly impact various sectors positively, its integration faces numerous and varied challenges. Overcoming these hurdles will require a multifaceted approach that includes technological innovation, policy support, and shifts in public perception. Summary of challenges. As we've explored throughout this discussion, hydrogen, despite its potential as a clean energy carrier, faces numerous challenges that have hindered its large-scale adoption. These challenges range from technical barriers such as high production costs and low volumetric energy density to societal hurdles like public perception and lack of cohesive policy support. Economic considerations, such as the financial viability of hydrogen applications in automotive, industrial, aviation, and energy storage sectors, also contribute to slowing its integration. Future prospects. The future for hydrogen is not without promise, however. Ongoing research and development could bring about much-needed innovations in hydrogen production, storage, and utilization, making it more cost-effective and efficient. Policymakers could further support this by establishing favorable policies, such as subsidies and tax incentives, designed to spur the hydrogen economy. Public-private partnerships also present a significant opportunity for accelerating hydrogen technology. Such collaborations could tackle challenges too large for any single entity to solve, such as infrastructure development and large-scale production and storage of hydrogen. As technology continues to advance, the hurdles that hydrogen currently faces may be significantly reduced or even eliminated, paving the way for its broader adoption across various sectors. As this happens, hydrogen could very well fulfill its promise as a cornerstone in the transition to a more sustainable and cleaner energy future. Thank you for joining us on this comprehensive exploration of the multifaceted challenges and the future prospects of hydrogen as an energy carrier. For more insights into renewable energy and sustainability, continue to follow ReneeEnergy.com. Thank you for choosing ReneeEnergy.com as your go-to source for all things renewable energy and sustainability. With our YouTube channel, we explore the latest developments and innovations in the field, including hydrogen fuel cells and the use of AI and machine learning to optimize energy consumption. If you're ready to take the next step towards a cleaner, more sustainable future, visit us at ReneeEnergy.com and discover the many ways we can help you transition to renewable energy. Thank you for watching and subscribing. Stay up to date on all the latest news and insights by subscribing today.